Okay, so for for this section, I'm going to have the graphing calculator out because you're really going to need it for almost every problem on this material. If you do not have a TI-84, or even a TI-83 would work. If you do not have one of those, you can get an app on your phone. They're really good. I've seen them. They work just like my on-screen app does here. It emulates all the functions of a TI-84. Just download the TI-84 app on your phone, then you get used to how to use it, get used to how to use the buttons on the calculator using the app, and then when you get to the test, you would just check out a TI-84 from the testing center. Just call them up ahead of time or pop in ahead of time and make sure they have one for you, because you're really, really, really going to need one. Okay, I just can't help it. You just need one for this level of math. It's just part of life. Okay, and so we're going to use it. In this problem, we don't need one, but for most of the rest, we will. Okay, so what does it mean to be a factor, first of all? If we think back to like when we were just dealing with numbers, factor just means you divide in evenly. So it divides evenly, no remainder. Okay, that's supposed to be an arrow, sorry. No remainder. So as an example with numbers, suppose I do like, I don't know, 2 times 3 times 5. What is that? That's 30, right? These are all factors of 30. How do I know? Well, first of all, that's how I built the 30. The 30 is really built from the multiplication of these 3 factors, okay? So that's what factors are. If you multiply the factors together, they build the quantity. The other way to tell, so how do I know? Like if I just give you a 30, how would I know if like 5 is a factor? Was 5 used to build the 30? We see that it is, right? But how would I know? So I would say, okay, I would do 5 divided into 30, and I would say, okay, that's a 6. 6 times 5 is 30. Remainder 0. Okay, so remainder 0. So that means 5 was a factor. Okay, and the other factors work out to 6, right? 2 times 3 is 6. So that's basically what factoring, or what factors mean in number world. But basically it's the same concept when you're dealing with polynomials. So for example, of the 3 of these, probably this guy is the hardest, the second one, because it's got the most complicated binomial that's being asked whether it's a factor. Okay. Also, this is of the type where we cannot use synthetic division. Why not? Synthetic division is only valid for 1x. You have to have 1x minus a quantity. Okay. So this would be like 1x minus -2. This would be 1x minus 1, etc. But for if it's more than a 1x, you cannot even use synthetic division. In fact, I don't personally like synthetic division because then you have to think, is this the right situation to use it or not? I just always use long division, and then I don't have to worry about anything. Okay? So what we're going to do is, just like this kind of long division like we do with numbers, we're going to do that same idea here with polynomials. Okay? So I'm going to take the 2x minus 7, and I'm going to divide it into, whoops, I guess I'm running out of room there. Let me clear that out. I'll just, hang on a second. Let me just erase. Okay? And so I'm going to take the 2x minus 7. I'm going to divide it into the 16x to the 4th. Again, we're doing the second little problem here. Minus 56 x cubed minus 24x squared. Let's see, minus 18x plus 357. Okay, so the first thing you do for long division, if you're not a long division person, is you say to yourself, self, because you want to be polite, right? Okay, so 2x divided into 16x to the 4th. Think about, how do you make the first term on the outside look like the first term on the inside? What do you multiply by? Well, how do you make a 2 look like a 16? You're going to need what? You're going to need an 8. 8 times 2 is 16. How do you make an x look like x to the 4th? You need another 3 copies of x. You ignore the second term. Don't worry about that initially. Just look at first term, first term. How do you make the first term on the outside look like the first term on the inside? Look at the numbers first. 2, make it look like a 16, you need an 8. Then you look at the x's. X to the 1, how do I make it look like an x to the 4th? You need 3 more x's. Okay? When you multiply back down, then you deal with both terms. 8x cubed times 2x should match that first term. That's how we chose the 8x cubed, right? So it better match. And then 8x cubed times the 7, right? 7 times 8 is what? 56, but negative. Okay, so negative 56, x cubed. Now, once we multiply back down, all of this has to be subtracted because that's been accounted for. The 8x cubed together with the 2x minus 7 is the 16x to the fourth minus 56x cubed. So this has already been accounted for by the 8x cubed. So I have to subtract it. We always subtract. When we multiply back down, we always subtract what's there. Now, a lot of students hate subtracting polynomials. They'd rather add. So if you're that type of person, a lot of people are, you can create an addition by just changing the signs. Right? Just take opposite signs. All right, so now let's go ahead and add this up. So what do we get? 16 plus negative 16 on the x to the fourth, those are like terms, get 0. Okay, negative 56x cubed plus positive 56x cubed, you get 0. That doesn't always happen. The first term should always go away because you chose this term in the answer so that it matched, so it multiplied down and matches the first term. So that first term should always go away. The second one going away, that's kind of unusual, but it did in this case. So the x cubes went away. So now let's keep subtracting. Okay, so I'm going to have negative 24x squared take away no x squareds is still negative 24x squared. Negative 18x take away no x's is still negative 18x. And then 357 take away no numbers is still plus 357. Okay, now, so then you say to yourself, okay, self, how do you make the first term on the outside look like this new first term on the inside? Okay, so how do I make a 2 look like a negative 24? And the answer is I need a negative 12. Now, how do I make an x look like an x squared? I need one more copy of x. Negative 12x times 2x is negative 24x squared. It better match that term, which it does. Negative 12x times negative 7. So negative times negative is positive. 7 times 12 is what? 7 times 10 is 70. And 7 times 2 is 14. So that would be 84. So positive 84x. And I'm going to subtract. If you hate subtracting polynomials, you can always go in and say, okay, I'm going to add the opposite. So I'm going to scratch this out and make it a minus. Okay? And so let's go ahead and add up, see what we have. And we have negative 24 of these x squareds plus positive 24 of them is gone. Negative 18x's plus negative 84x's is what? Negative 102, right? Negative plus another negative gets more negative. So you're going to have negative 102x plus, now the 357, there's no number term, so it just stays plus 357. And now you say to yourself, self, how do I make the first term on the outside look like the first term on the inside? How do I make a 2 look like a 102? I need to multiply by 51, and it has to be negative, because it really needs to be a negative 102. So I'm going to say, sorry, I'm going to say negative 51. I don't need any more x's, because I already have x to the 1 and x to the 1 here, so the x's are fine. 51 times 2, negative 51 times 2 is negative 102, and I have the x. And then negative 51 times 7 is positive 357. And I'm going to subtract all this because it's been accounted for. Whoops. And so I end up with what? I end up with 0, right? Because negative 102 plus 102 is gone. And then positive 357 plus minus 357, right? Because we're going to change the signs. Remember, we're going to go in and say plus and change the signs. So negative 102 plus 102 on the x's is gone. Positive 357 plus negative 357 is gone. So we have, yippee, 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 we have remainder 0. Okay, when we have remainder 0, we are happy, right? That means it's a factor. Okay, so the answer here is remainder is 0. So the answer here is yes, sirree, right? Okay, so you should be able to try these two. I would recommend just practice your long division, even though you can rearrange it for synthetic division. I just prefer to practice long division. That way I don't have to worry about whether it's the right situation or not. Okay, so remainder 0, it is a factor, right? Just like our good old example, like 2 times 3 times 5 was 30. If you divide any factor that is a factor of 30 into 30, like let's say I take the 2 into 30, right? I'm going to get a 15. If you multiply back down, you get remainder 0. Okay, but what if I tried something that's not a factor, like 7 into 30? What happens? You get remainder 2, right? When the remainder's not 0, it's not a factor. When the remainder is 0, it was a factor, right? 2 was a factor, and I can see it right here. Okay? Fun, 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 right? By the way, how would I continue this problem? Okay, to continue this problem, so I already know that I can rewrite this. I'm going a little bit beyond the problem here, but I know I can rewrite this problem now. This polynomial right here can be broken down into a 2x take away 7 times this quotient, times 8x cubed minus 12x minus, whoops, that's 12, minus 51. Okay, so to factor means to eventually get it so there's no more powers. And that's super important for algebra, and it becomes super duper important for calculus. Okay, to be able to factor, meaning break down a polynomial into multiplications of things so there's no more exponents. That becomes really critical, that skill. Okay? Okay, this is the next problem, problem 3. I guess this one we can also do without the calculator, but the rest is really going to need the calculator. Okay, so what is the rational zeros theorem? It says that if a function has a rational zero, what's a rational? First of all, what's a zero? A zero of a function is something that makes the function zero. So for example, if I just have like, suppose I had, for example, this is not the same problem, but suppose I have like x minus 2 times x plus 3. Okay, another way to write that would be x, if you FOILed it out, it would be what? X squared minus 2x and plus 3x would be plus x minus 6. So if I gave you either the factored version or the unfactored version, I can guarantee you that x equals 2 is going to be a zero of the function. How come? If I plug 2 in, it will make this function become 0. How come? 2 squared plus 2 is 6, right? Because 2 squared is 4, 4 plus 2 is 6, 6 minus 6 is 0. It works. How did I know? Because x squared plus x minus 6 really is these two factors multiplied by each other. Okay, the x minus 2 factor times the x plus 3 factor. So if anything makes the x minus 2 factor become 0, it will result in 0 times some other number, 0 times 5 in this case. Plug 2 in, you're going to get 0 times 5 is 0. Okay, so that's why it's making this, this is the FOILed out version. It's the same quantity, it's just FOILed out. It's going to make it 0. So if you make either factor 0, you make the whole thing 0. Okay, x equals negative 3 will also be a 0 because it makes this factor 0. Okay, let's check it. Negative 3 squared is 9. 9 plus negative 3 is 6, and 6 take away 6 is 0. It works. Okay, so these are your zeros. These numbers are your zeros. They make the polynomial 0. Okay, so a 0 is something that makes the whole polynomial become, a 0 is an x value or input value that makes the polynomial have a value of 0 when you plug it in for x. Okay, and they're important. So notice that to find the zeros, I really had to find the factors. To find the zeros, I had to find the factors. That's the idea here. We could factor this to find the zeros, okay? But it turns out there is a pattern that people discovered, a couple hundred years ago when they started working on this, about probably more like 300 or 400 years ago. But this has been important for a while. And the pattern is that if there is, these are called rational zeros because this is a rational number. This is 2. 2 is really 2 over 1. A rational number is a number that can be written as a whole number divided by a whole number. If you can write something as a whole number divided by a whole number, that's a rational number. This is also a rational number. Negative 3 over 1. Whole number over whole number. So these are rational zeros. The 2 is a rational number that works as a 0 of the function. The negative 3 is a rational number that works as a 0 of the function. Okay, these are rational zeros. What's something that's not a rational 0? Square root. Okay, like that's not a rational number. The decimal of that would go forever, as an example. This cannot be written as a whole number over a whole number. Okay, so if you can write it as a whole number, no roots or anything, over another whole number, no roots, that's a rational number. So these are zeros because they make the function 0 when you plug them in, and they happen to be rational numbers. If a polynomial has rational zeros, it doesn't mean it will, but if it does, this polynomial could, in theory, only have these kind of crazy irrational zeros. This would be an irrational 0. Irrational numbers cannot be written as fractions. Okay, so that would be an irrational 0. If it was, well, it's an irrational number. If it's a 0 of the function, it would be an irrational 0. Okay, that's an irrational number. These are rationals. If a function has, or if a polynomial has rational zeros, it will be, all those rational zeros will be of the form factors of the constant term the constant term is the term that is by itself, no x's, over, so I'm going to kind of create a bunch of fractions here, divided by factors of the leading coefficient. And our book goes into why this works, okay? But the leading coefficient is the number in front of the highest power, which is 1 in this case, okay? So what goes into 10? Plus or minus 1. 1 always goes into any number. Plus or minus 2 goes into 10. 3 does not. 4 does not. 5 does. And then 10 does. A number always goes into itself, okay? And then now for the denominator, we need the factors of the leading coefficient. The leading coefficient is 1. The only thing that goes into 1 is plus or minus 1. So all combinations of 1 over 1, 2 over 1, 5 over 1, or 10 over 1 with positive or negative signs can all potentially be rational numbers that are factors, or that are zeros of this polynomial. Okay, so if I list them out, it's going to be negative, it's going to be 1 and negative 1, then 2 and negative 2, and then 5 and negative 5, and then 10 and negative 10. Now this doesn't mean these are the zeros. These are all rational numbers, okay? Because a whole number is a rational number. Just think of it as being over a 1, and you can see it's a fraction. Whole numbers are fractions. It's just that the denominator is 1, so we don't think about it like that, but they are fractions, so they are rational numbers, right? These are rationals. Rational means it can be written as a fraction of a whole number over a whole number. So these guys are all rational potential zeros. They're not definitely zeros. These are rational numbers that are potentially the zeros of the function. If the function, so these are rational numbers that are potential zeros. They're not definitely zeros, but they're potential of the polynomial. Okay, I'll just write poly for polynomial. So, so for this polynomial that they gave us right here, if it has rational numbers that serve as zeros, those rational numbers will be within this list. If it does not have rational numbers, then c'est la vie, they're not in this list. Okay, so this list is the possible rational zeros. Okay, and that's going to help us later on. So you'll see why this becomes important on the next problem. All right, so let's go on to the next problem. Actually, let's just quickly do problem number 4 in the homework. Number 4 is just one more example of a rational zero question. So in this case, so my rational potential rational zeros are going to be what? I should say zeros, sorry. It's going to be factors of the constant term divided by factors of the leading coefficient. I'll write LC for leading coefficient. So my constant term is 7. Now what divides into 7? Either plus or minus 1 or plus or minus 7. That's the only thing that goes in. That's a prime number. 7's prime. So the only thing that goes into a prime number is the number itself and the number 1 and the number itself. Okay? How about the 3, the leading coefficient? Well, again, that's prime. So plus or minus 1, plus or minus 3, just 1 and the number itself. So if we form the fractions, you're either going to have 1 over 1 or 1 over 3. So 1 over 1 would be negative 1 or positive 1. 1 over 3 would be negative 1/3 or positive 1/3, because you can do the positive or the negative. Then you can have 7 over the 1, so that's going to be negative 7 or positive 7. I guess I didn't need the plus. I think it probably would take it probably won't count it if you put the plus there, but it is positive. And then the last would be 7/3, right? So it'd be either negative 7 over 3 or positive 7 over 3. So if this function does happen to have rational zeros, they'll be in this list, okay, which is interesting. Okay, so now we're on problem number 5, and now we're really going to start to get some good use of the calculator. So make sure you have your calculator app. If you're just watching this without the calculator or the calculator app, I can promise you, you're going to have a lot of trouble on these problems on the test. I'll say that again. If you're watching this without either a calculator, graphing calculator, or a graphing calculator app on your phone, you are watching something that's not going to help you. It won't help you very much. You need to get either a graphing calculator or download a graphing calculator app for your phone, a TI-84 app on your phone. Do it now. Otherwise, you're wasting your time on this, okay? You need that tool, okay? All right, so I'm assuming you have one of those. Otherwise, hit pause and go get it and come back, all right? So we want to find the zeros of this polynomial. Remember, like what we said before was, for example, remember when we did like x minus 2x plus 3, and we FOILed that out, and that was really what? X squared plus x minus 6. So if I asked you to find the zeros of this, what are the zeros of that? Okay, the way to find them is to factor. If you know the factors, this is a factor and this is a factor. If you know the factors of a polynomial, you know the zeros. How come? You set each factor equal to 0. When you set a factor equal to 0, you get a 0 of the function. Okay? Here's this factor equaling 0, so x equals -3. These are the zeros. Okay? That's a 0, and that's a 0 of the function. What is a 0? It's an x value that makes the polynomial 0. If you plug in 2 into this polynomial, it will become a 0. If you plug in -3 into this polynomial, it'll give a value of 0. So to find the zeros of a polynomial, you essentially need to know the factors. And then you set each factor equal to 0, and each solution of that will become a 0, a number that makes the polynomial 0. That's the key. This is called the relationship between factors and zeros. Very important that you really clearly understand this, because that's the basis of the entire rest of this portion of the course. Okay? Super important. Now, basically to get the zeros of the polynomial they gave us, we need to factor it. This I could have factored by myself. If I didn't know that it was x minus 2 times x plus 3 as the factors, I could have deduced that, because this is not too hard to factor by hand. But this one is not easy because it's not a quadratic. It's a cubic. It's third power. So anytime you go above second power, it gets difficult. Okay. So what we're going to do is we're going to kind of use our tools. So one tool we have is the rational zeros theorem. So notice, suppose I would have used the rational zeros theorem on this polynomial right here. Suppose I would have used the rational zeros theorem. Okay, so I would have had factors of the -6, which is the constant term. What are factors of -6? Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, right? Factors of the constant term over factors of the leading coefficient, which is 1, plus or minus 1. So if I do all my divisions, I would get what? 1 over 1, so either -1 or +1. 2 over 1, so either -2 or +2. 3 over 1, okay, so either -3 or +3, and then 6 over 1, okay, -6 and +6. So these are the potential rational number zeros. Remember, these are rationals because they're all fractions. They're really all divided by 1, right, if you want to think of it like that. They're all fractions, so they're all rational numbers. A rational number is something that can be written as a fraction. A whole number is a rational number. Now, are the actual zeros in the list? Let's see. Are these actual zeros in the list? Let's see. Is 2 in the list? Boom. Okay. Is -3 in the list? Boom. Okay. Do you have to say boom? No. You could say bing or bam too. Okay. But there they are. Okay. So we had 2 actual rational zeros, and there they are in my list. Okay. So this is just proving that the rational zero theorem does work. Okay. So now let's apply it to this bigger problem. Okay. So let me erase what I have here. And now let's apply it to the bigger example. Okay, so let's bring in the pen again, and we'll go with blue. So I want to find the rational zeros of this, which means I have to factor it. Okay, but that's difficult. So we're going to begin life with the rational zeros theorem. And this is how you should always approach these kinds of problems. Okay, so I need factors of 28 divided by factors of 1, because 1 is the leading coefficient. So what goes into 28? Well, 1 goes in, 2 goes in, Does 3 go in? 3, 6, 9, 12, 15, 18, 21, 24, 27. No, you just count by the number. It didn't hit the 28, so it doesn't go in. How about 4? 4, 8, 12, 16, 20, 24, 28. Yes, it goes in. Okay, how about 5? 5, 10, 15, 20, 25, 30. Nope. How about 6? 6, 12, 18, 24, 30. Nope. How about 7? 7, 14, 21, 28. Yes. And then the next thing that would go in would be a 14, and then the 28. How about the factors of a 1? Just 1. Okay? So that means that all of these ratios, all these possible ratios of a number from the top divided by a number from the bottom would be the potential rational zeros. If this function has a rational zero, it doesn't mean it will. Okay? It could have all like those kind of crazy square root irrational zeros. Okay? Or even imaginary so-called complex numbers as zeros. But if it has rational number zeros, they'll be on this list. Now, a fast way to check these, and here's where we're going to begin to use the calculator to speed things up, is go to your y equals menu. If you have something in there, clear it. Put in the original polynomial. So I'm going to put in x. Here's my exponent button to the third. Then make sure to go to the right to get out of the power. Okay, x cubed plus 10 x, and for squared it already has an x squared button, so I can save a little time. Plus 31x in my case, plus 28. Enter. Okay, so there's my function. Now I'm going to go to what's called table set. Very important to learn how to use table set. Second function, table set. The key is I want to be able to type in these numbers myself. I don't want the calculator choosing numbers for me. And the way to do that is your inputs are the independent variable. Outputs are dependent. I want to leave that on automatic. I want the dependent on automatic so the calculator automatically computes the values for me. But I want to choose the x's. So I go down and I go to independent and put that over to ask. So I can choose my x's. Okay, and now I need to go to a table. So second function, table, and I can type in my x's. Plus 1 and minus 1. Let's see if those are zeros. So I'm going to type 1 in. Nope, it's not a 0 because it didn't make the function 0. How about minus 1? Nope, not a 0. It didn't make the function 0. How about 2? Nope. How about negative 2? Oh, getting close. How about 4? Nope. How about negative 4? Haha. Okay, ding, 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 ding. Right, negative 4 is a 0. Let's just check the rest of them real quick. Maybe we get lucky and get 2 of them. Okay, so how about negative 7? How about 7 first? I like to do the positives first. Nope, negative 7. No siree. We could try the 14. We could try the negative 14. These look like losers. Right? I don't think the 28 is going to work either. They're just, the numbers are just getting crazy big. Yep. Okay. Crazy big. Okay. Like negative 14. Oh, hey, that's my bank account. Negative 14,000. Yep. There we go. Okay. But anyway, so it turns out the only rational 0 was the negative 4. Off this. Okay. So that means that negative 4 is a 0. Okay. So what we found was negative 4. X equals negative 4 is a 0. If that's true, and this is very important, that means x take away negative 4 is going to be a factor. Okay, so that's a factor of the function. And we can, of course, write minus a negative as plus. So x plus 4 is a factor. Okay, very important. That's what we just found. Now, if x plus 4 is a factor, that means it divides evenly into the polynomial. That's what factors are. So we can pull the x plus 4 out and see what's left. That's the next step. Okay, so I'm going to clear my writing here. Okay, let's bring the pen back. So we already know x equals negative 4 is a 0. If we want, we could plug negative 4 in, but the calculator did it for me. Okay, and so x take away negative 4 is a factor, which is the same as x plus 4 is a factor of the polynomial. That means if I divide x plus 4 in to the polynomial, And if you're a synthetic division person, you could rearrange, do this as synthetic, but I'm just going to always do long division so I never have to worry about is it the right scenario. Okay, so x cubed plus 10x squared plus 31x plus 28. Okay, so you say to yourself, how do I make the first term on the outside look like the first term on the inside? I don't need to change the numbers. The number's 1 out here and 1 in here, but I do need more x's. Okay, so I'm going to have an x squared. Multiply back down, x cubed plus 4x squared. Remember, we subtract that because it's already been accounted for. Okay, if you want, you can change the signs and add. Okay, I'm going to skip that. I'm just going to go ahead and subtract. X cubed take away x cubed is gone. 10 take away 4, that's minus 4. 10 minus 4 is 6. So I have 6 x squareds left over, and then plus 31x plus 28. Okay, how do I make a x on the outside look like a 6x squared? I need to take this 1 and multiply it by 6, by positive 6. To get the numbers correct, and then to get the x's correct, I need an additional power of x. Okay, when I multiply back down, 6x times x is 6x squared. 6x times 4 is 24x. We subtract. Okay, what do we get? Well, we get, trying to keep the same colors here, 6x squared take away 6x squared is gone. 31x take away 24x is what? 7x, right? Plus 28. Now, how do I make an x look like a 7x? And the answer is with a plus 7. 7 times x is 7x. 7 times 4 is 28, positive 28. Then we subtract, and I can see it's something minus itself, so we're going to get our good old buddy remainder 0. What does that mean? That we got a remainder 0? That means that we're happy because that means this was indeed a factor. Okay? So now what do I know? I know that my polynomial can now be written as, so I know that this polynomial right here can be written in factored form, at least partially factored, as x plus 4 times this quotient right here, this result, x squared plus 6x plus 7. Okay? So is it fully factored? No, it's only partially factored. Why? Because I still have squares left. Okay? But at least I'm partway there. Okay? Now, how do I factor it further? Well, with a quadratic, what we can often do is like try to factor it by hand. So I can try and go like this. I can try to say, well, we could try, xx. And for the 7, we either do positive 7, positive 1, like plus 7, plus 1, but that's going to give me an 8x in the middle, not a 6x when I FOIL it. Or we could try x minus 7, x minus 1, and that's going to give me a positive 7 as my last term. But if I FOIL it, I'm going to get negative 7x and negative 1x makes negative 8x. So neither of these work, and these were really my only chances of factoring by hand, which means I cannot solve this by factoring by hand. So unfortunately, I have to use quadratic formula. Okay, yuck, right? But hey, life's difficult sometimes, right? That's why not everybody gets a college degree, okay? Because it's a lot of work. All right, so let's factor it, right? So let's quadratic formula it. So I know my a is 1, coefficient of the x squared. My b is 6, and my c is 7. So by quadratic formula, I'm going to have x equals negative of the b plus or minus square root of b squared minus 4 times the a times the c, oops, sorry about that, whole thing divided by 2 times the a. So that's going to be negative 6 plus or minus root of, let's see, 36 take away 28 is what? 8, right? All over 2. So that's going to be, I'll work over here now, running out of room. So I'm going to have negative 6 plus or minus, now root 8. Remember, root 8, how does 8 factor? 8 is really 4 times 2, right? And then 4 is really 2 times 2. So I have 2, 2, 2. And an easy way to simplify a square root is remember that if you have all your factors, then if you have 2 of the same factors, you can cross them out, put 1 on the outside. Okay? So, and for third root, you'd need 3 of the same factor. For fourth root, you'd need 4 of the same factor. Okay? So it's going to be 2 root 2 for the root 8, all divided by 2. Now, can I cancel these 2's? Can I take this 2 right here and cancel it with this 2? Can I? If you said yes, you're falling into the single greatest trap in algebra. You can never cancel anything that's either adding or subtracting or plus minus onto anything else in the same fraction. If something's adding or subtracting to anything else in the same fraction, it cannot be canceled. Okay? If I let this 2 cancel this 2, then the 6 gets off for free. Okay? And I get the wrong answer. So I cannot cancel these 2's because the one on the top is being added or subtracted. So instead, we factor out a 2. If you want to cancel something, if you can factor it out, then it's cancelable. So if I factor a 2 out on top, negative 6 divided by 2 gives me a negative 3. Think of it as 2 times negative 3 is negative 6. If I pull the 2 away from 2 root 2 and put on the outside, I'm going to get plus or minus root 2, all divided by 2. And now these can be canceled. Why can these be canceled? Because the 2 on the top is only multiplying now because it was factored out, which means it's multiplying. So these do cancel. So I end up with negative 3 plus root 2 and negative 3 minus root 2. Okay, so those are my 2 additional zeros. So that's a 0 of the polynomial. That's a 0 of the polynomial. Notice these are not rational zeros. That's why they were not in the rational zeros list. Okay, they have unresolved square roots in them. They're not rational zeros. Okay, so how do I? So I found all the zeros. Okay, so I've already got the zeros. What was my first 0? The first 0 was the negative 4, right? Because this was really x take away negative 4. Remember how we built that? That was x take away negative 4. So my zeros are negative 4, then negative 3 plus root 2, and then negative 3 minus root 2. Okay, those are my zeros. What if it asked me for the factorization? It's not asking it, but it will in future questions, so let's just practice that. What about the factors? Let me try a different color here. What about the factors? The factors were x take away negative 4, right? If negative 4 is a 0, then x take away that negative 4 is a factor. So x take away negative 4, which is the same as x plus 4, is a factor. The next factor is going to be x take away negative 3 plus root 2. Kind of ugly looking, right? But it's a factor, right? Plus its parents don't think it's ugly looking, right? Okay, and then x take away what? Negative 3 minus root 2. And of course, if you want, you can distribute the negative. So I could write, this is really x take away negative 4 if you want to be fancy. This is was really x take away negative 4 here. Okay, so we can rewrite that as x plus 4. I can rewrite this guy as x plus root 3. I'm sorry, x plus 3, my bad, because I'm subtracting a negative, and then subtract the positive. So x plus 3 minus root 2. And this would be x, the minus times the minus is plus 3, and the minus times the minus is plus root 2. Okay, and then I had the x plus 4. Sorry to squeeze all this in on you here, but this would be how we would write out the factorization of the polynomial. I know it's kind of an ugly factorization, but it is what it is. Okay? All right, so let's go on, and let's see how we're doing time-wise. I usually like to keep these at about 30 minutes or so, so I'm going to go ahead and stop now and then open up the next one as a part 2. All right, there we go. Fun, 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 right? Let me Google that. Hang on. Yep, I just checked it on Google on my other screen, and yes, indeed, this is fun. Okay, Google says.